Hi guys, in this fourth NMR video I will work some of the practice problems in the handout. These practice problems early on will focus primarily and only on Proton NMR. So this first one, the goal here is to determine structure. Okay, formula is given here. In some cases down the road, you will not have formula. But formula is given here. And there's information that can be taken from the formula. For example, degrees of unsaturation. How many DOS are in this formula? C9, that would be 2N plus 2, 20. We're missing 8 hydrogens. Divide that by 2, 4. 4 DUS. That's good information. That tells us that the structure has, for example, 4 double bonds, or 4 rings, or a combination of those, such as 2 rings and 2 double bonds, etc. So, good place to start if you have formula. Alright, so let's look at the Proton NMR. We've got our baseline here. We have peaks. Some of the peaks are expanded. Okay, I may have mentioned this at the end of video 3 when we sort of introduced this NMR here, this practice problem. We can see the baseline for the expanded peaks. Okay, I would start right here. I see peaks here in the 7 to 8 region. By the way, let me point something out here. TMS, which this should be TMS here, singlet, is not exactly on 0 for some reason. That TMS peak should be on 0. All peaks have been shifted to the right a little bit. Again, I don't know if this is a computer-generated spectrum or a real spectrum or whatnot, but that peak should be on 0. That means really every peak should be moved down. That's about 1/4 of a ppm. So instead of this being like 7.1, it should really be about 7.4. Okay? The baseline has not been set exactly here. That's a little bit odd, but I wanted to point that out. But still, these peaks are in the 7 to 8 region. What type of protons give peaks here? And of course the answer, if you've been learning your peak positions, is these are aromatic H's. Okay? H's that are on an aromatic ring will give signals in the 7 to 8 region. Alright, well let's continue with this here. What's the most common aromatic ring? Well, the most common aromatic ring is a benzene ring. Alright, with H's on here. Now, could it be some other type of aromatic ring? Yes, it could. But the old adage says if you hear hooves, you want to think horses are running. You don't hear hooves and think zebras or antelope or something else. Let's think horses first. Let's think benzene ring first. That's a recommendation. Until we start having more advanced problems and maybe something exotic. And we can always revise this. Okay. Now there has to be substituents on the benzene. If it was just benzene, it would only have peaks here. By the way, the formula has 9 carbons. If it's a benzene compound, there's 6 carbons right there, and we only need to show 3 more to complete the structure. Now, one question at this point becomes, how many H's are on the benzene ring? There has to be less than 6 because one of these carbons has to have a substituent, at least one. But how many? Well, number of H's. That comes from your integration. And let's look at integration. We have integrals here, here, and I marked them at the end of the previous video. Okay? Now let's look at these. I'm going to get my ruler. Alright, I only have a large ruler. My smaller ruler is hiding from me. We can use this longer one though. Let's see here. That's 1 to 5. Well, no. 1 to about... I don't know, roughly about 4.5. We can also do this with the old finger method. It's about that long, okay? Well, it's almost twice as long as that. Well, let's look at these over here. Whatever this is, I'm going to go from 1 to 2.5. That's like about 1.5. Just in length here. I mean, what are the units? What are those? Centimeters? Okay. This over here is the same. It's more important to recognize that they're the same. And then this one seems to be longer. Okay. If we do it with just fingers, it's like boom, boom, but that's a little bit longer. If we actually measure it, it's like 2. And over here, this was like 4.5. Okay. Now you can't have a half a hydrogen, so it can't be 1.5 hydrogens. This is either 1 or 2. If it's 1, that means this is 1H, that's 1H. Then maybe that's 2. And that would be 1, 1, and 2 makes 4. But we have 12 H's in the compound. If this is only 4, that means this has to be 8. I doubt that's 8. So, instead, I'm going to say perhaps this is 2H. Now I'm going to write it here, and I could be writing in pencil so I could erase, but what if this is 2H? That means this is 2H, and then this is not double, because double would be 3, so it's not 4, but it's a little bit more, and this is 3H. Okay? And if that's 4 and 3, if that's 7 H's, then this over here must be 5 H's for a total of 12. All right? And I think that indeed is the integration, the relative integration. Now, this number, that means that each centimeter is a little bit more than an H, or 1H equals, well, we can do math here. That is 4.5 divided by 5 equals this looks like each H is 0.9 centimeter. 5 H's would be 0.9 times 5, 4.5 centimeters. Okay. Does this hold consistent across? Okay. If we're saying this is 2H, then it should be 1.8 centimeter. Well, it's close. I said 1.5. Okay. We can measure again. And you know, if we kind of, maybe 1.6, your integration is never going to be perfect. Okay? You have to sort of work with it. And often you identify, okay, how much is 1H? How long is it? Etc. I think we have 5, 2, 2, 3. Okay. Now, let's go with that. Now, if there's 5 aromatic H's, that means there's 5 H's on this ring. Importantly, that means there's just one substituent, or non-H. This leaves 5 H's on the ring. 1, 2, 3, 4, 5. Okay? This tells us we have a mono substituted benzene ring. Now, let's move down here. Before we do though, let me point out that I really didn't look at the splitting here. You really don't have to always. I went through how we determined this partial structure. Okay? That right there is a partial structure. What we're going to do is we're going to put all partial structures on the paper and then we're just going to link them together. Now let's move to the saturated CHs. Okay? Here we're going to have to use splitting and it will be very helpful. All right. The fact that it's 2H pretty much tells us that it's a CH2. All right. Now it could be two identical CHs. But let's think horses first. Let's go with CH2. That comes from the integration. The signal is for two H's. Two identical H's. These H's are going to be identical. They give one signal. But what will make it a triplet? This is thus a triplet 2H. This is a multiplet 2H. And this is a triplet 3H. 3 lines. Okay? If you can't see it there, it's been expanded for you here. What would make this a triplet? Well, the neighbors make it a triplet. It's bonded to a CH2. And that would be a triplet because it has two neighbors. N plus 1 is 3, triplet, and it's 2 H's. There you go. Now, I'm going to go over here to this triplet because a triplet is easier to deal with than a multiplet. Multiplet usually is going to come from complex splitting. Triplet. First off, it's a 3H. That means it's a CH3, most likely. What makes it a triplet? Neighbors. This is bonded to a CH2. And by the way, this CH2 has to be bonded to something else because carbon makes 4 bonds. Same thing here. CH3 here. So this is a triplet 3H. Okay. But hold on a minute. This compound has 9 carbons. We've shown 6, 7, 8, 9, 10 on the page. We have too many. We also only have one other signal, this multiplet 2H. It's a CH2. It's one of these. But actually these two, we have too many carbons. We have to get rid of one of the carbons. Let's get rid of one of these and make this CH2 the same as that. And what we have here is CH2, CH2, we have that. But the CH3 is just bonded here. And ultimately, the triplet 2H is here. Triplet 2H. This is a triplet 3H. But then this here is a something 2H. But this would be the multiplet because it's complex splitting. This CH2 splits the signal into a triplet. Then that splits each line of the triplet into a quartet, and you end up with 12 lines. Okay? 12 lines. If it's 4 lines, we call it a quartet. More than 4, we're just going to call it a multiplet. All right? The signals tell us that's what we have. Triplet, 2 triplets, One for 2H, one for 3H, and then the multiplet. Now you can look at the lines of the multiplet. Do we see 12 lines? Theoretically, we expect 12. You may not see 12. Here's the multiplet. I see 1, 2, 3, 4, 5, 6, 7, 8 lines. The reason we don't see 12 is because some of them probably overlap. Okay? And they're right on top of each other as opposed to separated. Okay? But it is certainly a multiplet, way more than 4. All right. We have this fragment, and we have this fragment. That accounts for the entire formula. C9H12 is all here. There's no oxygen, nitrogen, halogen, nothing else. The only thing we can do here is just bond these together. This needs a substituent, that needs a substituent. The answer here is propylbenzene. What else could it be? It's actually a pretty introductory NMR problem. We use splitting. We really didn't use peak position. I mean, they're all saturated. We were working in the saturated CH region. This signal is for these H's here, there, and there. This is benzylic next to the aromatic ring, so this is going to be downfield some. Okay, benzylic. We showed that earlier. Let's confirm that. Let's make sure we know where to look in the tables. Basically, like right here, this could be a double bond of an aromatic ring. The carbon bonded to the double bond, the H is there. Going to be down a little bit, 1.5 to 2. It's actually more down than that. Okay, peak position's never going to be exact like these tables. They give you some range. The range is often a little bit bigger. Well, here is kind of exact up there. Here they say 1.5 to 2.5. Could even be closer to 3. Again, you can expand these always, in my mind, a little bit further. Basically, I would say about 2 to 3. And indeed, the signals for this benzylic CH2 group is about 2 to 3. All right? But again, we really didn't need to use peak position here. Okay, so dealing with aromatics. When you hear hooves, think horses. All right, let's try another one. On the flip side here, no formula is given for this compound. But we do have an IR. Now, someone has done a little work for you and given you integration already. Boy, that was awfully kind of somebody. Integration of 2, 1, 2, 2, and 3. All right. Again, these came from a Bruce textbook. We're not using that textbook anymore. Good news, TMS is on 0, so we're back to where it should be. Let's take a quick look at the IR. What do we see? I see sp3ch But I also see sp2ch. A little small something here. Looks like an aromatic to me. Aromatic range. 1700. What is that? Looks like a carbonyl. Which, by the way, you're not going to see the carbonyl in the Proton NMR because there's no protons here. Okay? I mean, if you're just looking at the C and the O. Okay. Let's see what we have here. 7 to 8, what type of hydrogens here? Aromatic. Most common aromatic ring. Benzene ring. How many substituents on the benzene ring? Got to be something on the benzene ring to give these other peaks. And to give a carbonyl, I mean, we have no carbonyl here. This becomes a fragment, a structural component. Well, how many hydrogens are on this ring? We see 5 H's. Integration is given. It's different peaks. The first thing we need to look at here is how many aromatic hydrogens. It's 5, 2, 1, 2. That means there's only one substituent, and the remainder 5 H's, 1, 2, 3, 4, 5. It doesn't matter what the splitting pattern is. It has to be only one substituent. We have this fragment. Okay, what else do we have? This is a quartet. 1, 2, 2, 1. Quartet 2H. The 2 means 2H. This is a triplet 3H. Okay, quartet 2H. That means it's most likely a CH2. What makes it a quartet? How many neighbors does it have? Three neighbors. 3 plus 1 is 4, quartet. 3 neighbors, CH3. All right. Another bond has to be here. If this is the signal for that, there has to be a signal for this part of the fragment. Is there a signal for that? Well, this is the signal for that. It's 3 hydrogens. It's integrating for 3 hydrogens. It's one signal. It's a triplet. What makes it a triplet? It must be bonded to a CH2. And indeed it is. Quartet 2H, triplet 3H, this is a classical pattern for an ethyl group. And they're splitting each other. Now, do we just put an ethyl on the benzene ring and say the answer is ethyl benzene? If all we had was proton NMR, perhaps. But the IR shows us we have a carbonyl. We have 3 fragments. Do we have any other fragment? No other fragment that contains a proton, because there's no other signal in the proton NMR. What is this here? Could that be an NH? Well, think about it. If that was an NH, we should see that hydrogen in the HNMR. No. There's no other H. That's not an NH. That's not an OH. It's probably an overtone of the carbonyl. 1700 times 2 minus a touch. 3400 minus a touch. Likely an overtone. Both of these are accounted for either in the ring or the saturated ethyl group. 3 fragments. There's only one way to put it together. If we put the ethyl here, there'd be no place for the carbonyl, because you can't just put the ethyl and then add the carbonyl. No, because this structure has an H here. You can't just say there's no H, there's an H there. And if we add something there, this is no longer CH2, CH3. If you take an H away from here, this no longer matches. Okay? The answer here is to slip the carbonyl in between the benzene ring and the ethyl group. We maintain the ethyl. With the carbonyl, we maintain this fragment. Let's confirm this. With this CH2, let's talk peak position. It's about 3. What makes this move downfield to about 3? Next to carbonyl. Okay? Next to carbonyl, electron withdrawing, it's deshielding here because of this dipole pulling away. More deshielded. The CH3 signal is not as deshielded. And then the aromatics. There's our structure. And here the IR helped us because otherwise we would not really be able to tell that there was a carbonyl group here. Before we move on, students often give a number of incorrect structures. For example, let's just look at one. We might get this. This is a possible structure. The student says, I see an ethyl, I see a ring, and I see a carbonyl, and that's really the gist of it, and put this together. What's wrong here? First off, this structure has an aldehyde H, all right, and this is, if you remember, about 9 to 10 ppm in the Proton NMR, and that's simply not there. If there was anything there, it would have been shown. Simply not there. This structure also only has 4 aromatic H's. 1, 2, 3, and 4. But the NMR shows that we have 5 aromatic H's. Now you can also see the presence of aldehyde in the IR, and it's really not there. The aldehyde CH, if you remember the position for that. So it's really not that structure. Instead, it's this ketone here. Hey guys, we just solved that with pretty good certainty with no formula given. No formula. All right, let's try another. Again, no formula given. Determine the structure. All right, came from Bruce textbook. I see aromatic H's. How many? Again, integration has been given. All right. I kind of wish I didn't give you this integration so much. Oh, good. The next one you have to do integration on your own. All right. But how many aromatic hydrogens in this compound? 4. That means how many substituents on the benzene ring? Assuming it's benzene, assuming it's horses and not zebras. 2 substituents. Now, once we get 2 substituents, we have potential for isomers. And assuming, it depends on how much symmetry. I'll do this, I'll take a look at this assuming no symmetry. 2 substituents are different. They can be next door to each other. That's called ortho. We will learn this terminology during test 2. It's worth learning now. 2 substituents, 4 H's, 1, 2, 3, 4. Thought maybe I had this drawn already somewhere. We could also have these substituents can be, that's a 1-2 relationship. Here it could be a 1-3 relationship. This is called meta, a meta relationship. We can also have, finally, a third like this. That's drawn a little funny. Basically, they're opposite. It's a 1-2-3 1-4 relationship. It's 1-2. This is 1-3. It's 1-4. It's called para. And this is very important for understanding number of signals, and here we want to look at the splitting as well. This is doublet 2H and doublet 2H. It's 2 doublets. They've expanded it here for you to see it a little bit better. Doublet 2H, doublet 2H. And this clearly comes from the splitting. Question: which of these isomers here will give 2 doublets in the proton NMR? 2 signals with each of them being doublets. All right. I'll let you think about that. It's one of these. This clearly indicates which one it is. Let's move down here. By the way, let's take a quick look at the IR. It looks like aromatic. That makes sense because we have aromatic hydrogens. We must have an aromatic ring, and the IR confirms that. We have our good old sp3CH, sp2CH. But that makes sense because these are sp2CHs on aromatic rings, so that goes hand in hand. These are, looks like they're saturated CHs, so those are sp3CHs. Carbonyl. No carbonyl. Now, if we had carbon NMR, we could confirm that because the carbon of a carbonyl will give a precise peak in the carbon NMR. But based solely on the IR, it looks like there's no carbonyl. There's no OH or NH. There's no triple bonds. That's really all I see in the IR. Okay, let's look at these two signals. They're both singlets. Three H's. Most likely it's a CH3. Most likely this is a CH3. But we have to recognize these two methyls are not the same. That is, they're not the same by symmetry. Because they're giving two different signals. One of them is more downfield. Now, this is in that 3 to 4 region. What would make this signal for this methyl so far downfield, almost 4 ppm for a saturated CH? All right. Right here. The carbon with the H's must be bonded to some type of electronegative atom, such as nitrogen, oxygen, or halogen. All right. Well, it's not halogen, because if it was bonded to halogen, you'd be done. Because there's no other room to bond anything else there. If it's bonded to oxygen, this allows you another side to bond, because oxygen makes 2 bonds. Now, if it was bonded to nitrogen, you would have 2 additional places to bond. It's not halogen. Can we tell which is it, oxygen or nitrogen? Well, there's no formula given. You're not going to be able to tell. This was going to end up being an ether or an amine. You're not going to be able to tell that from IR. There's no carbonyl. But this CH3 it's got to be one of these scenarios for that CH3 to be downfield like that. But importantly, though, another thing, we already kind of answered it here, it's isolated. And what I mean by isolated is it has no NMR active neighbors. There's no splitting. It's a singlet. Nothing is splitting it. See, back over here, something was splitting this signal. And so we put a CH group, or it could have been an OH group or NH group next door. But IR showed no OH or NH. And we also had this signal here, which is CH3. Isolated. But this one here is also isolated. But this one, okay, I know the answer here. It's got to be oxygen, okay? This is bonded to an oxygen, but that one's not. This one's way downfield like this, bonded to an oxygen. That one must not be. Because if it was bonded to oxygen, it would be down here too. We've got this, and now we have 2 fragments. I've got a methyl and a methoxy. This is the X and Y that go on this ring here. The question is really, what is the substitution pattern? That's what we need to decide, and then we just need to put the 2 groups. I'll let you think about that one further. and we'll finish it up in class. All right. Now, I'll end here. How do we know it's not this nitrogen here? Because you don't have enough peaks here. If the other CH3 was on the nitrogen, then you would have two CH3s then you would only have one other place for the ring, but you need to be able to connect to the ring twice. So that doesn't match. The other thing is, if the nitrogen had two methyls, these are identical. That's just going to give one signal. That'll be a singlet 6H. All right, because of symmetry. All 6 of these H's are the same. That's one signal. We'll talk more about that. In fact, maybe the next NMR brings in the idea of symmetry there. We don't have a signal for 6H. And you can't say, well, it's an N-methyl and then there's an H, because there's no H in the IR, no NH in the IR, and there's no NH in the Proton NMR. This is an oxygen. The oxygen is moving this downfield. Okay, we'll finish that one up in class. Work on it, but take a close look at this. Very important. By the way, this type of analysis here was sort of on the first page, particularly number 5 here. Okay. Now the answer is going to vary. If the two substituents are the same, you're going to get a different answer here for a number of signals compared to when the two substituents are different. All right. But number 5, very important, very useful. Okay. So, I'm tempted to ask you to do this one on your own, because it's the last one before we move on to carbon NMR. Okay? Give you a chance to do this one on your own. Formula is given. Somebody is very kind. I would start with DUS, so we can get an idea of how many rings or something there. All right. You're going to have to determine your integration. That is the relative integration of your signals. All right, using this integral line, IR. And see if you can come up with structure. We have, okay, TMS. You got to be careful here. This may look like one signal. All right. It's actually 2. Because if it was one signal, why would you have this side sort of short and then tall? I mean, it's 4 lines, but that's certainly not a quartet. Quartet doesn't look like that. It's actually 2 signals here. They've expanded so you can kind of see that. And then we have signals down here. Okay, guys, give that one there a try from scratch. See if you can come up with structure. Then in the next video, we will move into carbon NMR, which begins here, and we'll see that carbon NMR is analogous to proton NMR in many ways. All right. A few sort of minor differences. The baseline is a lot larger. It goes from 0 to 200 ppm instead of 0 to 10 or 12. But we're going to use the 20 times rule to help us predict peaks based on what we already know for proton. Okay. And so there's not going to be as much introduction. And then we'll quickly start looking at carbon NMR spectra. All right. And things like talking about how to get better resolution. Okay. So our next video, which should be video number 5, I believe, we'll move into carbon NMR. And possibly fluorine NMR, a little miscellaneous stuff here at the end of the handout. Okay, remember guys, you also have the comprehensive spec problems in the workbook, and of course you have lots of problems in your Klein textbook, or whichever textbook you're using. Okay guys, that was video number 4.